Sir Isaac Newton was a scientist who lived from 1642 to 1727. He developed the three basic laws of motion and published them in 1687 in a 3-volume work called the Principia Mathematica. Newton's discoveries helped start a scientific revolution and led to the fundamental understanding of how bodies move through physical space. The first law of motion, the law of inertia. Objects will remain at rest or in a uniform motion in a straight line unless acted upon by an unbalanced force. Here we have 3 spheres on a table in a state of rest. The gravity pulling the spheres down is countered by the force of the tabletop pushing the spheres up in the exact opposite direction. The balance of forces is what keeps the spheres at rest on the table. This sphere will act as an unbalanced external force. Without another force to counter its movement in the opposite direction, it becomes an unbalanced force acting on the other spheres. The external force collides with the spheres and changes their motion state. The natural tendency of an object to remain at rest or in a uniform motion in a straight line is called inertia.
A bicycle lying on the ground stays like that until an unbalanced force, like you lifting it, acts on it. And a rolling bicycle keeps on rolling, and it will only stop if an unbalanced force acts on it. In this case, the combined friction from the ground and air is the unbalanced force causing it to slow down.
Wow! So without friction, it'd keep on rolling forever.
That's right.
The second law of motion, the law of force, mass, and acceleration. The acceleration of an object depends upon its mass and the magnitude of the force applied to it. When an unbalanced force acts upon an object, the motion of the object changes. The rate of this change over time is called acceleration. Acceleration depends upon 2 variables, the mass of the object and the magnitude of the applied force. In this example, a 3D character represents a pulling force on a 50 kilogram mass. Using his full strength, he has no trouble accelerating the object in the direction of his pulling force. If the mass is doubled and we want to accelerate it at the same rate, we must also double the force. Our character, however, is already pulling at his full strength. So what happens? He can only accelerate the object at half the rate as illustrated by his slower pace. This relationship between force, mass, and acceleration is the source of one of the most important equations in physics. Force equals mass times acceleration.
Second law says that a larger force will cause an object to accelerate faster than a small force will. If you're on a bike and a friend pushes you gently, you speed up slowly. But if she pushes really hard, you speed up really quickly, right? The larger the force, the faster the acceleration. Mass also plays a role. If we push a small child on a bike and then we push an adult, and we use the same size force in both cases, they will accelerate at different rates. The child with less mass will accelerate quickly. The adult with more mass will accelerate slowly. Now, these bicycle riders also have momentum, which is the product of the mass of an object times the object's velocity. You can actually feel momentum. For example, it's difficult to stop a moving object that has a lot of mass, like a bowling ball, or that is moving at high velocity. Here, try catching a fast baseball pitch without a glove.
Ouch!
So, tell me how Newton's second law of motion affects momentum.
Well, since the second law says an unbalanced force causes acceleration, which is a change in velocity, then force also changes momentum.
Excellent.
The third law of motion, the law of action and reaction. For every action, there is an equal and opposite reaction. A direct example of the third law is the rocket engine. Look at the hot gases streaming out of the shuttle's engines. If this is the action, what is the equal and opposite reaction? It becomes clear as the shuttle is propelled into the sky. The reaction to the gases escaping from the engine is the pushing of the spacecraft in the opposite direction. Everywhere you look are being followed by everything around you. With some extra awareness, you may begin to recognize your own use of these laws in your daily life.
Newton's third law of motion states that forces act in equal and opposing pairs. For instance, you push down on the ground with your feet when you walk. You may not realize it, but the ground in return pushes up against your feet. When a fish swims in water, its fins push against the water, and that's called the action force. But without the reaction force of the water pushing back against the fins, the fish wouldn't get anywhere. Even a bicycle lying on the ground is an example of this law. The bike presses down due to gravity. If the ground did not push back up on the bike with a force equal to the bike's downward force, the bike would just fall through the ground.
But it doesn't, because the two forces are acting together.
And that completes our lesson on Newton's 3 laws of motion. Now we know how forces act upon objects to influence motion, and we can move wisely through our world.